40 minutes.
Okay. Yeah. Okay. Before I start my my second part, maybe I shouldn't have I should have been faster, but I just wanted to tell you about this beautiful theorem, which is due to Procese, which and the reason for this is that I will have a generalization for this, if you can call it generalization, in the second part of my talks. So just so I'll just make a definition. So we have the data of an algebra, an algebra R, and a determinant law which goes from R to A. So this tuple is called the Cayley-Hamilton. Say that this tuple is a Cayley-Hamilton algebra. If for every element in R satisfies its own characteristic polynomial, which we just defined for determinant law. So for every R, so for technical reasons, we need to take every possible A algebra, but commutative A algebra, but it's not a problem. So here we define the characteristic polynomial to R, and like in the Cayley-Hamilton theorem, we apply it to R. So it gives us R to the D minus lambda 1 of R to the D minus 1 plus minus 1 to the D of R. And we want it to be 0. Okay, so every element satisfies its own characteristic polynomial. And the theorem that I wanted to tell you about is some sort of a converse to the Cayley-Hamilton theorem. Which is due to Procese in 1987. And so Procese, when he started thinking about these things, he was interested in the following question, which is and people problem as well, is that how can we determine if a given A algebra A can be embedded inside of a matrix algebra? So in another phrasing, when is a given algebra a sub-algebra of a matrix algebra? And this turns out to be a very difficult question for which we do not have a satisfactory answer. And but Procese remarked that if we add some extra structure, then we can have then we can have an answer, right? And in particular, if we add the data of a trace or a determinant law, so I'll phrase it in terms of determinant laws, but you can actually also phrase it in terms of the trace. So if A is if RD is a Cayley-Hamilton, so already one necessary condition for an algebra to be inside of a matrix algebra is that it satisfies the Cayley-Hamilton theorem, right? And the converse is that if an algebra satisfies the Cayley-Hamilton theorem, then it is a subalgebra of a matrix algebra. So if RD is a Cayley-Hamilton Q algebra, but the trick is that we want to work with characteristic zero coefficient, because the theorem actually in positive characteristic is false, which is a work due. I'm not even sure if it's false, but there's a new paper. There's a new work on the arXiv just a few months ago, which gives a counterexample. So Q Cayley-Hamilton Q algebra. Then there is an embedding from R to MD of B for some commutative A algebra B. compatibly with the determinant. Compatibly with determinant means that the determinant of, so this determinant law is sent to the determinant, the canonical determinant law here. Okay, so I also wanted to talk a bit about applications of this theory to the theory of deformation of Galois representations, but as turns out, I didn't manage well my time, so I will not do it. But if you have any question about this, let me know later. Okay, and now I can move to the part of my joint work with Julian Quast. So okay, so symplectic determinant laws. Okay, so A will be as usual, so a commutative algebra. And we will consider the following matrix, which is given by the identity. So 0, the identity, minus the identity 0, and this lives inside of M2D of A. Okay, and we define an involution on the symplectic involution on the matrices by the following. So M, the involution is given by multiplying J by the transpose of M and then by J minus 1. So this is an involution. It means that M of G is equal to 0 to M, and also M1, M2, G is equal to G, M1, G. Yeah, just an evolution. Okay, and in particular, if maybe the start of this work is the following remark, is that if M is equal to its symplectic, so is M is invariant under the symplectic involution, which means that M is equal to Mg. Then we can write M as 4 block matrices D, B, C, D transpose. And then we do the following calculation. So we multiply M by J. Sorry, I keep saying G. And we do the calculation directly, and we get minus BD minus D transpose C, which turns out to be the same thing as J times M transpose. But then J has the properties that J transpose is minus J, which is also its inverse. And so here we write minus transpose M transpose, and we can put everything inside, and we get minus MJ transpose. And that J is equal to minus transpose, which means that MJ is alternating. So if we pick an invariant matrix under the symplectic involution and we multiply it by J, we get an alternating matrix. And the thing is that for alternating matrices, we have the determinant has a root, a square root, which we call the Pfaffian. So for alternating matrices, we have the Pfaffian, and the is a square root of the determinant. The J squared is equal to the determinant of Mj, but the determinant of J is 1, so it's equal to the determinant of M. So in some sense, if M is an invariant matrix under the involution, then its determinant has a square root. And we also have the following lemma, which is an analog of the Cayley-Hamilton theorem, and which I call the symplectic Cayley-Hamilton theorem, which said that if M is invariant under symplectic involution, then we can define sort of a characteristic polynomial, which is like in the classical case, T times the identity minus M. So this is still a matrix which is invariant under the symplectic involution. So we multiply it by J and we take the fraction. And so this is a polynomial with coefficients in A. And then the symplectic Cayley-Hamilton theorem says that every invariant matrix satisfies its own Pfaffian characteristic. And so from these two observations, we will define what it means to be a symplectic determinant law. So the general objects that we will consider are algebras, A algebras with involution. And we write R plus to be the invariant elements in R by this involution. And we will also, due to technical reasons, we need to ensure that we can invert 2 inside of A. So the definition is a degree 2D symplectic determinant law is a pair dp where D is a determinant law from R to A. And we also want it to be invariant under the involution. So it's a star invariant determinant law of the degree 2D. And P will be a polynomial law, like we saw before, but not entirely defined on R, but only on the invariant elements by the involution. So like we said in the motivating example, so it's a polynomial law which is homogeneous of degree D. And we also wanted to satisfy the following properties. So the first one, like in the case of determinant laws, we want that P of 1 to be equal to 1. The second one, like in the example, we want that P squared is equal to the determinant law. And the third one is the technical condition that is not actually needed in many cases, is that actually we can define an ideal inside of R, which we call a Cayley-Hamilton ideal, which is by which when we quotient by this Cayley-Hamilton ideal, we get Cayley-Hamilton algebra, like the name suggests. And the kernel of D, there's also a notion of kernel, and we want this technical condition that the Cayley-Hamilton ideal lies inside of the kernel of D, so that we can quotient by this Cayley-Hamilton ideal. Okay, so when we look at the examples, like before, so by symplectic representation, I mean a morphism of A algebras with involution from our algebra with an involution to the matrices with the symplectic involution. So this is what I call a symplectic representation. And so if you have a symplectic representation, then we can define a symplectic determinant law, which is given like before. So, sorry. So we sent R to the matrices by our representation. So this lies inside of M2DB. And then we take the determinant like before. So this is the construction that we saw. It's the same thing. And for P, we just do the same thing. We take the image of the invariance under the involution. It will be in the invariance under the symplectic involution. And then we multiply by j like we saw, and then we take the Pfaffian. And so this gives us a symplectic determinant law. And maybe to show why this definition of symplectic representation is a relevant one is that if gamma is a group, and this is actually and gamma and rho is a symplectic representation, which means that it lands inside of GSP2D of A. So here GSP2D are the matrices in GL2D of A, such that when we apply the symplectic involution, we don't get exactly the inverse of M. That would be just SP2D. But since we have a general symplectic group, it will be the inverse of M, but up to a scalar. So there exists this lambda M for some lambda M, which is an invertible scalar. So this is definition of the general symplectic group. So as before, we saw that we have a group algebra, which is A gamma, and we can equip it with an evolution, which is given on elements of the group by the following formula. So we just so this is called the similitude. So this is called the similitude character. So we apply similitude character to the representation, and then we take gamma minus from gamma. And then by linearity, we can extend to all of R. And so our rho, so our representation rho will give us there is like the previous case, there is a correspondence between the representation of this representation with this similitude character and the representations, the symplectic representations of our algebra to the matrix algebra with the symplectic evolution. Okay, and like I said in the end of the first part of my talk, we can actually make an analog definition, which is that of symplectic Hamilton algebra. So symplectic Hamilton algebra is the data of this tuple, where so R star is an involutive algebra like before, and DP is a symplectic symplectic determinant law, and such that every element that is invariant under the evolution satisfies its characteristic polynomial. So such that for every R that is invariant under the evolution, it satisfies its Pfaffian characteristic polynomial, which is defined as before. So the Pfaffian applied, so this P applied to T minus 1. And we have an analog of the theorem of Procesi, which is the converse to the Cayley-Hamilton theorem. You have the converse to the symplectic Cayley-Hamilton theorem, which says that so if A is a Q algebra, so we also need to work in characteristic 0, because like I hinted before, the positive characteristic case might not be true. So so if we have a symplectic Cayley-Hamilton algebra, then it embeds inside of a matrix algebra compatibly with the involution and compatibly with the determinant law and with the symplectic determinant law. Hamilton algebra of degree 2D. then there exists a commutative A algebra B and an embedding which respects all the structures of symplectic Hanson algebras. And so this is the first hint as to why our definition is relevant, is the right one, let's say. And the other theorem, which is definitively a good motivation, is that we also have an analog of the theorem of Taylor and Chenevier, which is if K is an algebraically closed field, then there is a bijection, and R star is a root of K bar algebra. Then there is a bijection between semi-simple symplectic representations of our algebra up to conjugation, of course, and symplectic determinant laws. And this is as explicit as before. So given a symplectic representation, we can associate to it a symplectic determinant law. And yeah, are there any questions? Okay. And actually, we use these results to prove a bigger theorem. So we use both these results. Okay, so in fact, are used to prove the following theorem, which is an analog of a theorem proved in the GLN case by Wang Erickson. Which is the following. So there is a diagram. So I will not elaborate on the definitions of the symbols that I will write, but let me just say that there is a space of, so if you have an algebra, if you have an invertive A algebra R, then we can construct a space of 2D dimensional representations of R. So these are just like, it parameterizes 2D dimensional representations of R. And we can also do the same thing. We can also construct a space that parameterizes the symplectic determinant laws of our algebra. And we just saw that there is a natural map. So for every representation, we can get a symplectic determinant law. And actually, there is in geometry there is a and we also remark that so this map is not injective at all, because we can always conjugate by an element of the symplectic group, and we will get the same determinant. We can get the same symplectic determinant. So we need in some way to quotient this space by the action of the the symplectic group by conjugation. And so there is an operation in geometry that deals with this, which is called the GIT quotient. So the GIT quotient constructs the quotient of this space by the action by conjugation of SP to D or even GSP to D. So this is what we call a GIT quotient. And by universality of the quotient, or by this fact that this map does not see conjugation, we have automatically a map from this quotient to the symplectic determinant laws, and that we will denote by nu. And we can ask ourselves the question, how far is so we saw that, like in the Brown-Espet theorem, we have that symplectic determinant laws are pretty much characterize representation up to conjugation. So our question is, how far is this space from this space? Which actually, this space is very hard to understand, because it involves exactly quotienting, which is not an easy operation to do. And the theorem is that this map nu is actually an adequate homeomorphism. And an adequate homomorphism means that it's a universal homeomorphism, which means that it is a bijection of topological spaces up to base change. And the second one is that it's a local isomorphism around points of characteristic 0. So whenever we have a point that is of characteristic 0, this map is going to be an isomorphism in a neighborhood of this point. And so this means that these spaces are not very far from each other. In fact, an adequate homeomorphism also means we can translate this to saying that it is in some sense power surjective, and the kernel of the map between the two is going to be locally nilpotent and Z torsion. Yeah. Okay, so I think I will stop here, and yeah, if you have any question about this or what I said before, I'm happy to answer.